Let's see if this is working. I am streaming right now live, reading what is going on here to see if I am indeed live. I'm probably live. I'm probably live, for sure. Okay, I'm live here. Okay, now I'm definitely live. All right. Hello, India. Namaste, Sastrikal. How is everybody going? I see some people in the chat room. That's nice. So people are coming in today. Hi. Hi, I'm very glad to be here. Okay. I'm very happy to be on this channel. No sound. There's no sound. There's got to be sound. Sound, right? Tell me if there is sound. Someone in the chat. No sound. No voice. Okay. There is no voice. You can hear me. You guys can hear me, right? No voice. Okay, let me see what the deal is. How about now? There's no voice. You can hear me. Now sound is good. You guys can hear me. Sound is fine. Okay. All right. Sound is fine. All right, so today I'm going to talk about the math behind deep learning. I'm going to talk about the math behind deep learning. That's what I'm going to do because deep learning is the technology of this year. It's a technology. It is the way to make money. It is the way to be successful in this new globalized world. Check this out. Check this out. It is now India's turn, okay, in the global economy. It is time. Now is the time for India. And what I mean by that is the more knowledge you have in this economy, the better off you're going to be. The better off financially you're going to be, the more access to resources, more people will respect you. And deep learning is really that technology that is the most important technology of the internet age. So if you understand deep learning, your life will be better and you will have more access to job opportunities. It is just all of software will become deep learning. It is that important. So what I'm going to do is I'm going to show you how a basic neural network works. And along the way, I'm going to talk about the mathematical pillars behind a neural network. That means I'm going to talk about probability theory. I'm going to talk about calculus. I'm going to talk about statistics. Okay, and I'm going to talk about linear algebra. Now, if you don't know these terms in detail, that's okay. That's okay. It's going to be a very basic overview. All right. So people keep saying there's no sound. Seriously? Sound is fine. There's got to be sound here for sure. There is sound. No one can hear me. Are you serious? All right, there is sound. All right, there is sound. There is sound, right? Okay, so sound is fine. All right, so what I'm going to do now that we have sound is I'm going to just look at this. Code. All right, so here we go. So okay, no problems. Okay, guys, we have to look at this code. So let me look at this code, and then we're good. We're good. We'll look at the code. All right, code time. Screen share. Share. All right. Check this out. So what I'm going to do is I'm going to talk about this neural network right here, and I'm also going to have this video of me right here in the corner. All right. Okay. So here we go with this. All right. Getting sound, good. All right, so here we go with this. So, so this is a basic neural network, right? So the basis behind deep learning is neural network technology. Neural network technology is what deep learning is. So when we take a neural network, and a neural network looks like this. This is a neural network. This is a neural network. This is a neural network. If we take this neural network and we give it lots of data and we give it lots of computing power, then it's going to be able to do it's going to be able to outperform any other machine learning model by far. It's going to be able to outperform any machine learning model. And so this is an incredible algorithm. This is an incredible algorithm. So we need to understand how this algorithm works. So what we're going to do is we're going to build this. We're going to build a 2-layer neural network in Python, okay? And that's all it's going to do. So what a neural network does is it learns the mapping. It learns the mapping between two sets of values, an input and an output. And so when you think of a mapping is just a map. It's like for these x values, what are the y values, right? So if you have a 3, then the y value, the associated y value will be -1. If a 0, it's going to be a 0. If a -3, it's going to be 0. So there's always a mapping. And we can represent a mapping as a function. And the function could look like any number of things. But a lot of times, a very simple mapping will be linear, which means the function will look like this, where you have y equals mx plus b. If you're familiar with algebra, that is the equation for a line, okay? So what is the function? That is what a neural network is trying to do. It's trying to find what the function is going to be. All right, so that's what we're going to do. And let's start off by looking at the x and y values here. So for the x values, we have a series of zeros and ones, right? These are zeros and ones. And for the y values, we have a series of zeros and ones as well. So we want to learn the mapping between these two. Like for any given triplet, like 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, what is the associated y value? And so the associated y value would be 0. It could be 1. It could be 1. It could be 0, right? So there's always some mapping between these triplets and the y values. So then what we want to do is create some kind of model where if we feed it some new triplet, like let's say, 0, 1, 1, it's going to know the mapping is going to be to either a 0 and 1, right? There is a pattern here that we want to learn. Neural networks are all about pattern recognition, recognizing what the patterns are, right? So we get this part. We have input data x and output data y. And so we can frame it a bunch of different ways, but really it's just, a function that's trying to learn a mapping. Okay? And let me also say a little bit more about myself as well. I think I forgot about that part, saying a little bit about myself. So let me go back to me. Okay, so let me say a little bit about myself. I am Siraj Raval, okay, and I teach deep learning on YouTube. I did a course with Udacity, which was awesome, and I am living in Amsterdam. This is where I am right now. This is my home. This is where I record stuff. Yeah. I'm living in Amsterdam. I was born in the US. I'm coming to India next month. It's going to be a lot of fun. And yeah, but I love deep learning. I teach deep learning at Udacity, and I teach machine learning. It's going to be a lot of fun. I'm coming to PyData Delhi, and then I might go to TEDx Mumbai. We'll see how it is. But I'm very interested in this technology, and I make a bunch of videos of it on YouTube if you search my name, Siraj Raval. Okay, so let me also, if you guys have any questions, feel free to answer. Feel free to ask questions, and I'll answer them as well in the chat. Okay, yes, I know Hindi. मेरा हिंदी बहुत अच्छा नहीं है, लेकिन मेरा अंग्रेजी, yeah. So let me go back to this now. Okay, screen sharing time. All right. So we talked about our inputs and we talked about our outputs, right? And so now we're going to print them out. So we print them out, right? These are just arrays like that. These are matrices. Okay, so we have input and output data. So our next step is to build this neural network, right? We want to build the neural network that I was talking about. It looks like this. So the first part is for us to define the number of epochs. And what epochs are they're the amount of times we want to train our network, right? So 1 pass, 2 pass, 3 passes. How many passes? We want 60,000 passes. That's in total, that's what we want. Okay, so the topic is to learn the mapping between the input and the output data, right? The input data and the output data. That's what the topic is. And the more we can, this is a very basic example, but if we learn how to do this, Then we can move on to more amazing things like generating images, classifying images, generating video, classifying video. There's a lot of data that we can learn to detect anomalies in, financial transactions, who's the fraud. There's so many applications. But let's just try to learn this simple mapping first. So we have our input and output data. We've defined the number of iterations we want to train for, 60,000. And we'll also initialize our weight values. And so what do I mean by weight values? So notice that both of these are matrices, right? Sin 0 means synapse 0, and sin 1 means synapse 1. So we want to have these matrices that are initialized randomly. So these matrices are full of random numbers. It doesn't matter what they are, but they're random numbers. And what these matrices are they represent these lines. These lines are the matrices. So you're like, okay, what do you mean by that? Let me talk about this. So I'll get to what those are. But we've defined these matrices, and let's skip this function for a second. I'll go back to the function, and let's just get right to training this model. Okay, so let's get right into train this model, and then I'll talk about what everything is. Okay, so the first thing I want to talk about is training the model. So when it comes to training the model, we have a number of epochs that we want to train for. Let's say 60,000. We defined it up here, 60,000 epochs. And what we're going to do is we're going to feed forward. Okay, so we're going to take our input data, x, which is up here, and we're going to say that's going to be K0. And then we're going to do input times the first synapse matrix. And then we'll apply a nonlinearity to it. Okay, so now let me talk about the magic of what's happening here. So a neural network is essentially just a series of matrix operations, right? So when it comes to matrix operations, we have input times weight, input times weight, activate. So it's essentially just we're applying a series of matrix operations between input times weight, and then we're applying an activation function to it, and we repeat that process over and over again. All right, so input times weight, and then activate. It's kind of like a rap. Input times weight, activate, right? So you just repeat that over and over again. And so what happens is, if we take, and the weight values are randomized here. These are random weight values. But if we do input times weight, and then if we do input times weight, you might be wondering, why are we multiplying our input by these random matrix values? What significance do these matrix values have to our input? They're just random numbers. Well, what we're going to do is we're going to learn what the optimal values are for this matrix. That's the whole point of learning. We're going to learn what these values should be. So right now, we'll say input times this random matrix value, and then we'll apply what's called a nonlinearity to it. And a nonlinearity is going to be the sigmoid function, which looks like this. Okay? And so the sigmoid function looks like this. And this is the equation for it that we've looked at programmatically. And what a sigmoid function does is it takes a number that you input into this x value, and it's going to output a value between 0 and 1. And that value is going to be a probability value. We want the probability that this value is going to be is going to be a value that is going to be correct, right? We want a probability value that's going to tell us how likely the output is to be either a 0 or a 1. That's what we want. So we'll say input times weight, activate, and that's going to give us a probability value. So the math that I'm talking about here, this dot product is linear algebra. That's what people mean when they say that deep learning requires linear algebra. The dot product is essentially the same as multiplication in algebra. The difference between linear algebra and algebra is that in linear algebra, we define rules for multiplying sets of numbers instead of single numbers. So instead of multiplying a single number like 3 times 4, how do you multiply a set of numbers like 2 matrices? Well, you use what's called the dot product, which is basically multiplication, but for matrices. And that's where linear algebra comes in. And so we apply this nonlinearity with the sigmoid function to convert this result into a value, a probability value between 0 and 1. And so that's where probability comes in. And the reason we call it a nonlinearity is because neural networks can learn both linear and nonlinear functions. They are universal function approximators. They can approximate any function value. we apply this nonlinearity to it for two reasons. One, because it outputs a probability for us, and two, because it lets our neural network learn not just linear functions, but nonlinear functions as well. That means any type of function. Neural networks can learn any type of function. So we'll do that series of operations and get the first layer, and then we'll take that first layer output and do the same exact thing again and multiply by the next synapse weight, and then apply a nonlinearity to it and get the output value. And so when we look at this picture of a neural network, right, what's happening here is these three values are our triplets, that 1, 0, 1, right? Those values that were right up here. That's our input, so we call it the input layer. And then when we multiply the input by the first weight matrix, which is this, that's what these lines represent. They're the dot product. We're multiplying every single number in the first matrix, 0, 0, and 1, by every single number in this weight matrix or synapse matrix. And the result is going to be a series of numbers, 4, that represent the hidden layer. And so the hidden layer is K1. That is the result. It's a series of numbers. And so when we do the same exact thing again for the next layer, K2 is our output. And that means we apply those matrix operations again, and then we get an output value. And so the output value is going to be a value between 0 and 1 that tells us whether the output is 0 or 1. Given this set of inputs, 0, 0, 1, the output is going to be a likelihood that it's going to be either a 0 or a 1. Right? But all we did was we multiplied it by these random matrix values. So how is that supposed to tell us that this is going to be a 0 or 1, right? These are just, we just took our input and multiplied by random matrix values. What correlation does that have with our input? Well, the answer is that we're going to learn what these optimal weight values should be. So what we'll do is we'll calculate an error. And so we know what the actual output should be. We have those labels, right? Y. These are the actual outputs. And so when we take the actual output and subtract the predicted output, we get what's called an error value. And so the error value is the difference between our predicted output, K2, and our actual output, which is the Y value. And so we have some measure of how bad our neural network is at predicting the output. And that is the error value, okay? And so what we do is this whole thing, this whole process right here is called forward propagation, because we are in order multiplying our input by each of these weight matrices and then taking the result and multiplying it over and over and over again, forward, until we get an output. We compute an error. And so now is the real magic of neural networks. This is called back propagation, okay? We did forward propagation, and now we're gonna compute backward propagation, which means we're gonna take this error value and use it as a signal to help us update the values of our weight matrices, so that the next time we input a new value, it's gonna predict the best, most likely output. So we're going to use this error value to update our weight values. So the way we do that is called back propagation when applied to neural networks. So when I talked about the math behind neural networks, the first part was the dot product. That is the linear algebra. And the fact that we're computing probabilities using this nonlinearity, which is the sigmoid, that is the probability aspect. And now I'm going to talk about the third pillar, which is calculus. So we take this error value and we compute the derivative of the error with respect to our weights. We use this if deriv equals true statement to compute a derivative value. So that is the derivative of the sigmoid, which looks like this. So if we compute the derivative, that gives us what's called the gradient value. So if we take the derivative of our error, and then we multiply it by if we take the derivative of our last layer and multiply it by the error, that gives our gradient value. And so the gradient represents a direction that we want to update our weights. How should we best update our weights so they are optimal, so that the next time we multiply an input by these weights, it's going to be able to tell us what the optimal output should be. So that's our K2 delta value. Delta means gradient. So this is our value that we're going to use to update our weights later. The gradient tells us how far off the weight matrix was, at least this weight matrix. We have two weight matrices. And how do we update those matrices? So we'll do that again for the first weight matrix. We did it for the last weight matrix. And so now we're going to go backwards to the first. That's why it's called backward propagation, because we're backward propagating an error value. So this technique is called gradient descent, but in the context of neural networks, it's called back propagation. So we take and then we multiply it by the first synapse to get the K1 error. So how much did the first layer to the next layer's error? And then we do the same exact process again to compute the gradient for the first layer. And so now we have these gradient values for both of our layers, right? Our hidden layer and our first layer. And that is, we can use both of them to update our weight matrices, right? So we'll do the dot product of the layer times the gradient value, and then we'll add it to our synapse matrix. And that is back propagation. We forward propagated our input, and then we forward propagated our input. We computed an error, how far off are we? And then we backward propagated that error value to then update our weights. And so the first time we do that, it's only going to make our weights better by a little bit. But guess what? We're not doing it just once. We're doing it 60,000 times. What that means is every single time we do this, our weight values are going to get better and better. Look at this. This is printing out the error at every iteration, or not every, but every 10,000 steps. You'll notice that the error is decreasing every single time. What that means is our network is improving in its capability to learn. All right, so that's the essentials of deep learning. I mean, that is a basic neural network that can learn the mapping between input and output data. Now, if you know this, you can apply this knowledge to then a whole bunch of different tasks: stock price prediction, game bots, you know, art and music, and all sorts of scientific pursuits, learning from climate change data, trying to predict the future. But that's the basics of neural networks. And so now I'm going to go back to me. And yeah. So yeah, that was my presentation on some of the math behind deep learning and neural networks. And I'll answer any questions that you guys have now. So if you have any questions, let me know. And also subscribe to my YouTube channel as well, Siraj Raval. If you search my name, I'm on YouTube. Hit subscribe, the red button. But can I use Hindi? Mera Hindi acha nahi hai. But I do speak Gujarati, but I guess that's not super popular. But anyway, any other questions about deep learning that you guys would like me to answer? I will answer any questions. Just ask them in the comments. I am coming to India. It's going to be fun. And yeah, I rap about deep learning. Hindi is the question. What else in Hindi? Hindi, yeah. Hello. Yeah. So that is going to be it for this live session. So thank you guys for watching. And if you want to see more, you know where to find me. I'm here on YouTube. So bye.